Hi everyone, welcome you to the presentation of this video, analog electronics on DC biasing for bipolar junction transistors or BJTs. Okay, so under this biasing, we're going to look at the number of configurations, and we're starting with the first one, which is the easiest. This one is the fixed bias configuration. So a fixed bias configuration actually, it's a transistor which is biased in such a way. So a transistor has got three terminals. It has a terminal which we are calling a collector, which is this one here. And then it has another terminal which we are calling the base, which is that one there. And it has the emitter. So the base obviously is connected there. The emitter, that's where the arrow is, and the other one is called the collector. So if we are to bias this one under fixed bias configuration, it will look something like that. You're going to connect a resistor on the collector, and then that resistor connected on the collector, you're going to call it RC, which is just the resistor connected to the collector. And then you excite it with some voltage. So we are exciting the collector. That's why we are calling it VCC. So VCC was just picked as a term to show excitation on the collector. Then in that resistor which is passing through the collector, there is a current actually there is a current passing through the collector resistor, and that current we are calling it IC, or collector current. Then we are going to connect another resistor on the base. So these circles are just points of connection, and you're going to give it excitation as well, VCC. So we have this resistor which we are calling RB, or the base resistor. There's a current passing through there which we are calling IB, or current passing through the base, and we are exciting this one with the excitation voltage which we are calling VCC. So VCC is just the excitation voltage actually. We excite both the base as well as the collector like that. So these are coming in like that. Then they are supposed to go to the ground through the emitter. So we have some voltage here between the base and the emitter. The voltage we are calling it VBE. That's the voltage between base and emitter. And we have the voltage between the collector and the emitter. That voltage we are calling it VCE. Then this is supposed to be grounded, going to the ground. So on the emitter, that's where we connect the ground. So we're supposed to have a current passing through the emitter, going to the ground there. And that current we are calling it IE. So a configuration which looks like this is what we are calling a fixed bias configuration. You need to take note of the following formulas. So for you to have the emitter, if current is leaving the emitter, then it's supposed to enter through the other terminals. So emitter current is leaving, that's why you are having collector current and base current entering. Therefore, emitter current is basically a summation of base and collector current for all the transistors. So this type of a transistor is a NPN transistor. NPN, the arrow points outwards. For the PNP, the arrow points inwards. But for now, we are not going into those details. We're just looking at configurations. Then another formula you need to note is the relationship between the collector current and the base current. So collector current is basically beta. Beta is a constant which will be given times the current passing through the base. Or alpha. Alpha is also a constant which will be given you times emitter current. So you can express collector current in terms of base current or emitter current by that relationship. Then if you've got a voltage called VBE, this is basically the difference between voltage in B minus voltage in A. So voltage in B is the base voltage minus voltage in the emitter, VE. You have that. If you had a voltage called VCE, VCE is this voltage here. So VCE, the same thing applies. It's basically the difference between voltage in the collector minus voltage in the emitter, which is this one there. Okay. So for you to bias such a transistor, which is a fixed bias configuration, you need to take two routes. You can either take this route, VCC coming from here, passing through the base, and then it goes to the ground like that, or you can take the other route there. From there, it goes straight like that, and then it goes to the ground. So we'll start with this one. From there, it goes like that, passing through there, and then it goes to the ground. If you have to pick that one, of course, that's our transistor with those terminals. And it has those voltages, of course, but our interest is this side, so we may not show the VCE. So you have VCC there, which is the exciter, and then you've got a resistor RB, which is that one there, and then from there it's going to the ground. which is that one there. So what we've done is this configuration, we are just concentrating on this part, which is this one here. So once we have this, it's very easy to derive the formula. So you're not supposed to memorize anything here. If anything, there's something to memorize, maybe this, but it's straightforward. You may not need to memorize as well. So it's this. So this voltage, as it comes from the point of excitation, you are going to have a voltage drop across the base. You're going to have a voltage drop here, which we are calling VBE, and then it's supposed to go to the ground. But the one thing you need to note is that VBE is 0.7 for all the transistors. This one they may give you or they may not give you, but whenever you see VBE, just know it's a constant of 0.7. So from here, let's derive an equation. You realize that we have VCC, which is the exciter. As it goes to the ground, it's going to drop. So there will be a voltage drop there, which is a product of that current and that resistor, which is this one. And then there is another voltage there, VBE, which is 0.7. You have that. So taking this root, you are going to derive that equation there. So you don't need to memorize this. Just know which root to take, and then you can easily come up with that equation. Okay. Or you can choose to take the other route from VCC there, you pass through the collector. So those are the terminals. You realize that you're going to have VCC as the exciter there on top. And then it will just drop across that resistor. And there is a voltage drop there, which is VCE. This one is not a constant. It will be changing depending on the values of all those parameters. Okay. So we have this. So from this, it's very easy to derive the equation. You know as well, this voltage drop VCC is going to drop across that one, and there, that's when it will go to the ground there. So with that, you're going to derive this equation. VCC is basically summation of the voltage drop across the resistor on the collector, which is IC, RC, IC being that current and RC that resistor. And you've got VCE, which is this one. You have that. So we've derived these two equations. Pick that root, you're going to have that. Pick that root, you're going to have that. And then you can solve for whatever they're asking for. So on the next slide, we're going to look at an example. Okay, so questions will be coming like this. When they give you a question on biasing configurations, they will have capacitors. But in DC biasing, we are not going to be considering capacitors, because DC, whenever DC comes, if it looks at a capacitor, it sees an open circuit. So this part will be out. Even here, as it comes there, it will go there, of course, but this side, it will not go because of that capacitor to see an open circuit. So all the capacitors, you're not going to be using them when you're doing a DC biasing, because they are just open circuits. DC doesn't see a capacitor. When it looks at a capacitor, it looks at a window actually. So they are saying determine the following for the fixed bias configuration shown below. So this is a fixed bias configuration because you've got resistor connected on the base, resistor connected on the collector. You've got this VCC, okay? It's just been bridged, but it's either taking that route or that route like that. Beta has been given to be 50. So they want us to determine IB and IC, the value for VCE, VB and VC, as well as VBC. So let's look at the solutions there. So we're going to start with this path. We can pick these routes going to the ground with the equation we had derived. So picking that route, we have that transistor like that. It has those terminals, the base, the emitter, and the collector. But our interest is just through the base and the emitter. So with that route, we are saying you've got the resistor RB there, and there's a current passing through there, which we are calling IB. And then that's when it will pass to the ground using the emitter current like that. So with this, we said we would derive that equation, which we did in the previous case. So from this one, we are looking for IB. So here you realize that we have almost everything. VCC we have, they are saying it's 12 volts. RB is the resistor on the base, which is 240 kilo ohms. VBE, I said, is a constant, this one, to always be 0.7. So this is 0.7. What we want is IB. So from this one, you make IB the subject of the formula. You're going to have that. Then in there, I just need to substitute the given values. So where there's VCC, you substitute VBE as well as RB, you're going to have that. So RB, it's 240 kilo ohms. Kilo is 10 to the power 3. So this is like 240,000 ohms, which is this one there. When you evaluate that, you're going to have the value for IB as 0.00004708 amps. So this is the current which is passing through the base. It's as easy as that. And for the collector current, there's a relationship I gave you. I said collector current can be written in terms of base current as well as emitter current, but we are not interested in the emitter current. So for base current, we are saying collector current is beta times IB. Beta, it's been given in the question, it's there, this is 50. IB is the one from calculating, which is there. When you substitute there, you're going to get that as the value for your collector current. And then we look at VCE. So VCE can be found by taking this path, because this is where there is VCE. Okay, so with that, you have your transistor like that with terminals collector and emitter. Of course, there is a base, but we are not interested in the base for now. So you have VCC there being the exciter. There is a resistor there, RC, resistor in the collector, and the current passing through there, which we are calling IC. There is VCE there, then that one will go to the ground passing through the emitter current. So with that, we have derived this equation. VCC is dropping on collector as well as on VCE. You're going to have that. What are we looking for? We are looking for VCE. So in here we have everything. VCC, we have it, it's 12. RC is the resistor in the collector, which is 2.2 kilo ohms or 2200 ohms. VCE is what we are looking for. IC, we're just from calculating IC, which is this one. So we make VCE the subject. If you make VCE the subject, you're going to have that. Then just substitute the given values. You have that. Therefore, VCE will be 6.83 volts. Okay. Then we look at VB and VC. So if you look at C, that's what we are finding. You're saying VBE is basically the difference between voltage in the base minus voltage in the emitter. So in here, you realize that our emitter for a fixed bias configuration, there is no resistor there. It's a grounded one. Therefore, it's a 0 volts. So VE, or voltage in the emitter, it's 0 because it's grounded. So where there is VE there, we are putting a 0. So in that equation, if you make VB the subject, you're going to have VB is equal to VBE plus VE. VBE, we know it's 0.7. VE is 0. When you substitute, you're going to get the value for VB as 0.7. Therefore, you can conclude to say for a fixed bias configuration, the value for VB and VBE will always be 0.7. It's not gospel truth for all other configurations. This one only works for a fixed bias configuration. And then we can look at VC. VC as well. It's coming from VCE. VCE is the difference between VC minus VE. When you do that, you want VC, of course, you make it the subject. You're going to have VCE plus VE. We know VE is 0. VCE, we're just from calculating, which is this one. Therefore, what is VC? VC will be the same as VCE, which is that one. Okay. And then next, we are going to look at D, which is VBC. So VBC is the difference between VB and VC. We have those values. When you substitute there, you are getting that, and the value for VBC is going to give us that. So this ends the presentation on a fixed bias configuration. I'm going to look at another type of configuration in the next lecture.